Before we discuss gravity in detail, we need to give a firm background into Kepler's laws. And Kepler's laws give us how a planet orbits its host star, or actually how any two objects orbit each other. And actually, this is a very good example of the difference between a law and a theory. Kepler's laws just hold true. They are correct every time we observe orbits of just two objects in non-relativistic. We don't take relativity into account. But if two objects are orbiting each other and they're not massive enough to take general relativity into account, then Kepler's laws hold. They don't tell us why the objects orbit the way they do, they just tell us that they do, and that's what a law is. The theory, Newtonian gravity, will describe why the objects behave they do, but Kepler's laws just give us the behavior of the objects. Right? And Kepler was looking at the orbit of Mars in particular. He was looking at data of all of the known planets at the time. He lived in the 15 and 1600s, and he was trying to determine the orbit of Mars. And he had one of the most brilliant insights in all of science. And up until that point, everybody that had been working with planetary orbits had simply been assuming that objects orbited around the sun in perfect circles. And try as he might, he could not get perfect circles to fit the orbit of Mars perfectly. And he had, in a moment of brilliant insight, the stroke of idea that instead of trying to look at orbits as circles, what if I looked at them as ellipses? And an ellipse is a more general shape than a circle. A circle is actually a very particular type of ellipse. So here we have an ellipse, and the difference between a circle and an ellipse is a circle has a specific center, whereas an ellipse has two spots that we call the focus or the foci. Right? So each one of these spots is known as a focus. And the closer and closer these two foci are together, the more perfectly circular the shape is. And the more further apart they are, the more ovular the shape is as well. Now, the orbit does indeed have a center, but what happens in the ellipse, at least as far as orbits are concerned, is that the sun is at one of the foci of the ellipses, and there's not anything else at the other, nor is there necessarily anything at the center. So as far as a planet in an orbit around the sun, all that we have to care about is that the sun is at one of these foci. Right? And that's exactly what Kepler's first law states. It states that orbits are ellipses and that the sun is at one focus. Now, the Earth's orbit is almost perfectly circular. It has just a little non-circularity to it. We call that non-circularity ellipticity. It's slightly, eccentric, eccentricity. It's slightly eccentric. Okay, and eccentricity is a measure of how non-ovular the orbit is, right? So this is what Kepler's first law, and when he started working with ellipses and he finally found one that worked, it worked perfectly for Mars's orbit. And Mars was one of the most notorious orbits to try and determine in the ancient world. Again, the only known planets at that time were Mercury, Venus, Earth, Mars, Jupiter, and Saturn. Okay, and so those are 6, and of course we live on the Earth, so only 5 were visible in the sky. So during Kepler's era, during the era that he lived, the Renaissance, only 5 planets were known. And Mars was one of the most persnickety of those planets. And so we see from Kepler's work that all orbits are ellipses, okay, and that the sun hangs out at one focus. Now, also, and I should mention that this flies in the face of Greek thought, because Greek thought indicated that all planetary orbits must be perfect circles. The Greeks really liked the idea of perfection, and the circle is a perfect object. And so all planetary objects, if the universe is perfect, then the orbits of everything must be perfect circles, or at least some sort of perfect solid, some sort of perfect geometric shape. And an ellipse is nothing like a perfect geometric shape. There's actually a lot of symmetry here, but as far as where the sun is located in relation to where the object, planet, comet, whatever it could be at any given time, there's very little aesthetic symmetry as far as the Greeks are concerned. So breaking from this thought of perfect circles into the idea of ellipses was a very big step. I need to reiterate that very heavily. And his second law is equally just as impressive in its scope of breaking with tradition. And his second law says that orbits will sweep out equal areas in equal times. Now, this is also revolutionary because if objects orbit in perfect circles, then it would also stand to reason that their speeds don't change. An object's speed can't change, or else its motion is not perfect. And this particular statement of Kepler's second law says that these speeds can't be the same. So here's what Kepler is saying. If I look at an object at some initial time, we'll call it t1, and I look at the object at some final time, call it t2, then the object has moved from here to here, and it's swept out this red region. Okay, it's swept out the area of that red region. All right, and what this is indicating is that the closer the object is to the sun, the faster it's going to move. So then if I look at the object when it's on the opposite side of the sun, right, and I look at an equal time interval, we'll call this T3 and T4, and so the difference between T1 and T2 is going to be the same as the difference between T3 and T4, but because the object is further away from the sun, it's not going to be moving as fast. If it doesn't move as fast, it doesn't move the same distance in arc around its orbit, and therefore its speed changes. But it changes precisely such that if I look at equal time intervals anywhere in the orbit, then these areas, the red here and the purple here, these areas are going to be equal. That's what we mean by sweeping out equal areas in equal times. If I look at equal time intervals, then the closer the object is to the sun, the more arc it's going to sweep out, and further away from the sun, the less the arc is going to sweep out. But notice that these legs of this triangle are longer, so I have a smaller base but longer legs, and here I have a larger base but shorter legs, but the actual area themselves is going to be equal. And finally, Kepler realized there was a very important relationship, and we use Kepler's third law all the time in modern astronomy. And this law simply says that the square of the orbital period, we denote the orbital period as either capital P or T, depending on the text you're reading, but it says that the orbital period squared is proportional to the semi-major axis cubed. Now, what is the semi-major axis? So, in the ellipse, the distance through the two foci from one end of the orbit to the other, right? The longest line, the longest straight line I can draw through here, we call that the major axis, all right? So, if I draw from the center of my ellipse out to one edge, then that is half of the major axis, and that's what we call the semi-major axis. Okay, so the semi-major axis is half of the major axis, which is the longest distance you can draw through the two foci from one end of the orbit to the other end of the orbit. Now you can see, if I pull these foci together and I make my ellipse a circle, then the semi-major axis is actually just the radius of the circle. So for a perfectly circular orbit, the semi-major axis and the radius are the same. So Kepler realized this law after playing around with the plots of the object's relative distances and the object's periods. They knew the relative distances. They didn't have a way to anchor the total distances. That came later in the 1700s. But they knew how far relatively away the planets must be. And Kepler realized there was a strict relationship here. So what this is saying is that the square of the orbital period, how long it takes a planet to complete one orbit, the square of that time is proportional to the cube of that distance. All right? Now, again, these are all just laws. They don't explain why the square of an object's period is proportional to its semi-major axis cubed, nor does it explain why the objects sweep out equal areas in equal times, nor does it explain why orbits in general are ellipses. That all would come with Newtonian gravity. So in the next video, when we introduce Newtonian gravity, we will introduce the reasons why these must be true. We actually won't go into the derivations. They involve a lot more detailed mathematics than we have now. But do understand that the introduction of Newtonian gravity, you can actually explain all of these three theoretically from his law of universal gravitation. That is why Newtonian gravity was such a powerful tool, and still is a very, very powerful tool in physics and astronomy today. All right, we'll see you then.